And I want to start out with let's start with carbon. Let me zoom in on that. So for carbon, can somebody tell me what this 6 represents on the periodic table?
The number of protons.
Number of protons, which corresponds to also to the number of electrons in a neutral atom, right? So if it's not an ion, protons and electrons are equal. And then this number down here, what does this number represent?
The mass.
The atomic mass. Good. So when you look at carbon, the mass that you see right here is actually an average of the isotopes for carbon. So carbon exists as 3 different isotopes: carbon 12, carbon 13. I'm sorry, 2 isotopes: carbon 12 and carbon 13. But the number you see right here is an average. Let me go back and look at another atom. Let's look at boron. So boron atomic number is 5. That means there are 5 protons, 5 electrons if it's neutral. And then the atomic mass is 10.81. So we're going to work through an example today where we see how this atomic mass is actually calculated. Because this is, again, the number you see on the periodic table is an average of all boron isotopes. Boron can exist as boron 10 or boron 11. So let me switch over to my iPad, and then we're going to kind of work through some examples dealing with these isotopes and atomic mass. All right, so we're going to start out with that topic. So isotopes and average atomic mass. All right, and today is the 9th. All right, so let me first talk about ways to illustrate isotopes. Right, so magnesium exists as 3 different isotopes: magnesium 24, 25, and 26. So if we have the element magnesium, the way you will see this written, if you're talking about the isotope, is you'll see the atomic mass here and the atomic number here. Right, so this is Z, which is the atomic number. And then this is A, which is atomic mass. All right. And then if you wanted to write the magnesium 25 isotope, you would write it the same way because it's the same element. It just has a different atomic mass. So you write it magnesium, and it'd be 25 up here, 12 here. And then the magnesium 26 isotope, you would write it 26 and 12. Notice the atomic number is not changing, only the atomic mass. Right? Only the atomic mass is changing. And how do we account for the difference in atomic mass? What causes that to change? If the atomic number isn't changing, what does that mean? If the atomic number stays constant. Think about it. This number is, we just looked at the periodic table and somebody told me that the atomic number was the same as the number of what?
Protons?
Protons. Right, so if the atomic number doesn't change, let me get mine. So the atomic number is constant. What does that mean for the protons? Are we adding or subtracting protons?
No.
No, we do not, right? So if the atomic number is constant, the number of protons stays constant. All right. But what is changing to go from 24 to 25 to 26? What are we adding to the atom to increase its mass?
Neutrons.
Neutrons. Good. So with the change in atomic number, let's say going from 24 to 25, indicates the addition of a neutron. I'm sorry, the change in atomic mass. I think I said atomic number. Right. So when we change that top number, that atomic mass number, it means we've added neutrons. Right. We don't touch the protons, and the electrons don't have enough mass to contribute overall to the atomic mass. So anytime you're dealing with atomic mass, you're dealing with a change in the number of neutrons that are in addition to the protons that are already present. All right. So now let's switch gears a little bit. Let me cut this out. And let's talk about atomic mass. All right, so your atomic mass is, again, a sum of the protons and neutrons in a molecule. So you see that represented as Z, which equals right, the number of protons plus the number of neutrons. You can always figure out one of those values if you have the other two. You can figure out the number of protons if you have the number of neutrons and the mass. You can figure out the number of neutrons if you have the protons and the mass, and so on and so forth. But the Z value that we see on the periodic table is an average. It's not just one number for one particular element, because every element has what we call naturally occurring isotopes. So the Z value on the periodic table is an average of all of the masses of all naturally occurring isotopes. All right, all naturally occurring isotopes. So that number is an average, right, of those isotope masses. So we're going to talk about that. I think I misspelled occurring this morning. I'm embarrassed by that. That's okay. There's no spell check on Notability, but it's great. All right. The term or the phrase naturally occurring matters, because what that means is that you need to be able to find these isotopes in nature. Not, they can't be synthetic, or they can't be something that was developed in a lab. All right. So when we talk about naturally occurring isotopes, there is a calculation that we can do to find the average atomic mass. So the average atomic mass is determined by knowing the fraction or the abundance of the isotope and its mass. So we'll take, it's going to be the sum of the fractional abundance. And I'm going to explain that in a minute. So the fractional abundance times the isotope's mass. All right, so it's the sum of these two numbers. So the fractional abundance is the percentage of an isotope, right? If we're talking about it in nature. So it's the percentage of an isotope. And then the mass of the isotope is a known number. Right? As a matter of fact, there's a ton of scholarship and a ton of research that's gone into determining the atomic masses of isotopes as well as the average masses of each element in the periodic table. So every number you see in the periodic table, every atomic mass is an average of all the isotopes of that element, right? So let's start out talking about one element we just looked at, which is boron, right? Has a symbol of B, periodic table symbol of B, right? You can show this in the isotope form as B11 with an atomic number of 5, or B10 with an atomic number of 5, right? Somebody tell me for B11, how many neutrons are in that atom or in that isotope, sorry.
10.
Neutrons, think about it. The atomic number is 5 and the mass is 11. And the atomic number is a sum of protons and neutrons. Right? So we can always find out the number of neutrons by taking A, which is the atomic mass, and subtracting Z from it. So think about the alphabet going from A to Z. A is the atomic mass, Z is the atomic number, and then that'll give us the number of neutrons.
So it's 6.
6, yes, good. So B11 has 6 neutrons. All right, now you get another chance. What about B10? How many neutrons are in B10?
5.
Excellent. So 5 neutrons are in B10. The only reason I bring that up is because all of these different little nuanced calculations go together. When we talk about the atomic mass and the number of neutrons and the number of protons and distinguishing between the two protons and neutrons, you know, we need to be able to manipulate these numbers pretty quickly. All right. So here's the question. Let's do, because we're going to do an example with boron. So boron 11 has a natural abundance of 80.1%. So that what that means is that if you dig up a sample of boron from some mine, 80% of that boron in that sample is going to be the boron 11 isotope, which is so that means that most of the boron that exists in nature exists as boron 11. As you can tell from the periodic table, that boron's atomic mass is 10.81. That's the average. So that's closer to 11 than it is to 10 because we can round that up. All right. So then boron 10, which is an isotope of boron that has lost a neutron, the natural abundance of that is 19.9%. So you have a sample of boron that you dig up. Is going to consist of those two isotopes, B10 and B11, right? So the question now is, let's say that we're going to calculate the average atomic mass. I'm just going to abbreviate that. So calculate the average atomic mass. So we're going to use this formula up here. It's the sum. So you got 2 isotopes, so you have to do this twice. It's the sum of the fractional abundance times the isotope mass for each isotope. All right, so for B11, let me give you the numbers so you can, and make sure you got your calculators out. So the average mass is going to be equal to, for B11, we're going to turn that percentage. We're going to go ahead and turn that into a fraction or decimal. So we're just going to divide it by 100. So that's going to be 0.801. And then for the second one is going to be 0.199. Are we okay with that? All right, so we just take that percentage and divide by 100, and that'll give us the fraction form of it. And that's what we use in the equation. All right, so for the first isotope, we're going to use that number 0.801 times the mass of that isotope, which is 11.0093 atomic mass units. All right. And then the second isotope, we're just going to add that. So it's going to be plus 0.199 times that mass. Let me shrink that down just a little, which is 10.0129. And that's also measured in AMUs. Can somebody get that first number for us? 0.801 times 11.0093.
I got 8.818.
Okay, good. 8.818 AMU.
Yes.
All right. And let me fix that up so that it actually looks like AMU and not hieroglyphics. All right. And then what about the other number? 0.199 times 10.0129.
I got 1.992.
So 1.992.
Yes, sir.
All right, we'll take that. And then we're gonna just add those two numbers together to get, should put average atomic mass. Let me fix that up here too. All right. What do you have? Anybody got it yet?
10.811 AMU, sir.
.811, and we're going to report it like it is on the periodic table. If you'll notice, on the periodic table, all of your atomic masses are reported in 4 significant figures. So we're just going to report it as 10.81. So the average atomic mass of boron is 10.81. And again, that is determined by the percent abundance or the fractional abundance of one of the isotope times its mass. And it's the sum of those numbers. So if you have, let's say you have 5 naturally occurring isotopes, then you'll have 5 terms in this calculation. Each one would be a product plus the product of the other one, plus the product of the other one, so on and so forth. We're going to do one that has 3 terms to kind of make more sense. Any questions about this? So this is our equation that we'll use when we're talking about average atomic mass. It's the sum of the fractional abundance times the mass of the isotope. And that, depending on how many isotopes you have, that's how many terms you'll have in that sum. All right. Questions? Any questions? All right. Let's do a second example, and then we're going to do one other example where we actually have to find the abundance. Because sometimes this can be presented as you can have all the isotope masses and the fractions and just solve for the average atomic mass. Sometimes you can have the average atomic mass and the masses, but not the fractions. So these problems are presented one or two ways. And so the strategy I just showed you was when you have everything, the masses as well as the percentages. All right, the next example we do is going to be similar, right? We're going to do the average atomic mass for magnesium and its isotopes. So magnesium exists as three different isotopes. It's magnesium 24, magnesium 25. I just showed you this, but it's okay. And magnesium 26. Again, note the atomic number is not changing, only the atomic mass. Right, magnesium 25 has a natural abundance of 78.7%. And what you'll notice if you look at the periodic table, most of that, the number, the atomic mass is closest to the isotope that has the largest fraction, the largest percent, that makes up the largest percentage. So if you look at the periodic table at magnesium, that atomic mass is going to be closer to 24 than it is to 25 or 26. All right, so this is 78.70%. And then for magnesium 25, this is 10.13%. And then magnesium 26 is 11.17%. These are the abundances, right? And we can turn those into fractions with no problem. Just divide them by 100. So this is 0.7870. I'll make that an 8. 0.1013 and then 0.1117. All right, so you need them to be fractions so you can apply the equation. Right, you don't want to put the percentages in, but if you do, then you just have to divide by 100 at the end, and that's an extra step. So you might as well just convert them into fractions first and then stick them into the equation. All right, so the average atomic mass is going to be what? How do we set this up? What am I missing? So it's the fractional abundance, 0.7870 times what? What other number do I need in that equation? I can't calculate the average mass without a mass, right? So the 78% corresponded to magnesium 24, which has a mass of 23.98 AMU. So it's going to be that plus 0.1013 times magnesium 25, which is 24.99 AMU, plus 0.117 times 25.98 AMU. All right, so this is this is magnesium 24, 25, and 26. These are the three isotopes of magnesium. So we just need to calculate the numbers. So can somebody calculate the first one, and then somebody else do the second one, somebody else do the third one, and you can just unmute and let me know what it is. All right, anybody got the first one yet?
Is it 24.76 something?
Okay, we'll take it. You said, wait a minute now. You got, is that the whole thing, or is that for that isotope? 0.7870 times 23.98. It should be less than 23. Because that's like
My
taking,
fault. I put plus. I'm tripping.
that's all, it's all good. So it's like taking a percentage of 73. So that'd be 78. I'm sorry, 23. So it'd be 78% of that. So it should be less.
Is it on 18.87?
Yep, 18.87 AMU plus, somebody give me the second one, 0.1013 times 24.99. Excuse me. Okay, I see it now in the chat. Thank you. 18.87 for the first one. Let's get that second one. All right, let's see. 2.531. Yep, I'll take that. Thank you. Let's see. All right. And what about the third one? You can put it in the chat, or you can unmute and say it.
Is it on 3.03?
For the third one, 0.1117 times 25.98. It's a little bit less than 3. It's like a taking 11% of 25. So 5% of that would be 2.5. So it's got to be a little bit more than 2.5. So it's 2.902 for that one. For 25.98 times 0.1117. All right, 117. Sorry about that. All right, appreciate it. Appreciate it. I see it in the chat now. Thank you. All right, so we're just going to take the total of those numbers, and that's going to give us the average atomic mass for magnesium. How do you pronounce that? Is it Anye?
Yes, sir.
Okay. Go ahead and give us the total because you're on a roll.
24.303.
Okay. And we're going to report this in 4 sig figs because that's how it's reported on the periodic table. So we're just going to say 24.30. All right. And that's for magnesium. You can check it. If you look at the periodic table, can somebody tell me what that number is on the periodic table? Did you say 303 or 305?
No, I said 3.
Okay, all right. Anybody, could somebody tell me, verify that and look at the periodic table and tell me what the mass is, the atomic mass for magnesium, second column, first element in the second column, all the way to the left.
24.31.
24.31. All right. So when we take these average masses and we're taking the isotopes that's closest, or let me not say closest, the atomic mass on the periodic table is going to be closest to the isotope in the highest abundance. So let me write that down. So it's going to closely match the isotope with the highest abundance. Right, it makes sense, right? If we're doing an average, the larger number in that sum is going to be the one that dominates the average, right? So that's why when you see those numbers, the fractional abundance, the highest fractional abundance, that's going to be the isotope that the atomic mass matches the most. All right. So we got one other example, and this one is a little bit more tricky. And the reason it's trickier is because this example that we're getting ready to do, it doesn't have any abundances, no percentages, no nothing. We have to go and we got to find that. So the example is for chlorine. And chlorine on the periodic table. Can somebody tell me what the atomic mass of chlorine is on the periodic table? It's in all the way to the right, the second column, second to last column, and it's the second atom. Right underneath fluorine. Anybody got it?
Is it 35.45?
Yep, we'll take that. So 35.45. Actually, I'm gonna take it out one more. See, so 35.453 AMU. That's the average. Come on, let's tighten up. That's my average, right? But the naturally occurring isotopes for chlorine, there are actually two. There's chlorine 35. We're gonna call it isotope 1. And it has a mass of 34.96885. The second isotope is chlorine 37.
Mhm.
And that has a mass of 36.9 0.9590. All right, so we got the masses, we have the average, but we have no fractions. So here's the trick to these types of problems where you don't have the fractions is you have to remember that all the fractions have to add up to 1. So in this case, we're going to have 2 fractions, right? Because we got 2 isotopes. So if it's a fraction, it must add to 1. If it's a percentage, it has to be 100. And that's going to be the strategy for solving this problem. All right. So we're going to set this up by saying we're going to use our equation. So we'll take the average atomic mass, and that's going to be equal to the sum of the fractions or fractional abundance times what? What's the second term in that product? It's the fractional abundance times what? The mass of the isotope. All right. So we know the mass, we just need to solve for or find the fractional abundance. So the way we're going to set this up, since we only have 2 terms, we're going to make one fraction x. One fraction is going to be x, and let me fix that up. And this is a strategy that you can employ on any problem like this. This is going to be fraction 1. And then the other fraction will be 1 minus x. That'll be fraction 2. Because remember, both fractions have to add up to 1. So if I find x, and if I subtract x from 1, then that's going to give me the second fraction. Is that clear? Are y'all following? Anybody not following? So we can set this up. So let's take the average atomic mass, which is 35.453. And we're going to set that equal to 36.9659. And then that's going to be times x. I'm sorry, 1 minus x, my bad. It's going to be times 1 minus x. And then that's going to be plus 34.9688. Let me make sure I got the right numbers. 885 times x. All right. Any questions about that? So we're just going to make the x term the term that's closest to the atomic mass. Because again, that number is going to reflect the largest fraction of isotopes. So we're going to make that term x 34.9 is closest to 35. So we make that x, and then the other isotope 37 will make 1 minus x. Is that okay? Everybody good? All right. So we need to distribute this term. All right. So this is just this times that, and then that times that. All right. So we end up with this equation that looks like this. It'll be 34.9688 36.5x plus 36.9659. Is that right? That's that times 1 minus 36.9659x. Yes or no? Everybody's quiet. Again, when we're talking about those fractions, one is x, one is 1 minus x. It doesn't matter what two isotopes you're looking at. If you don't know the fractions, that's the setup. Make one of them x, make the one closest to the average mass x, and make the other fraction 1 minus x. Actually, I'm gonna put that in here. Right, because x is going to be a larger number than 1 minus x. So the one that's closest to the average mass, that's what you make x. The other one you make 1 minus x. Doesn't matter what two isotopes you're looking at. All right. Is that the distribution part? We good with that?
Yes, sir.
All right. And this is equal to 35.453. And again, this setup is ubiquitous. Once you learn how to set this up, you can set it up for any atom that has, or any element that has two isotopes that you want to solve for the fractions if you have the masses. All right. So now we can combine the x terms. So we're going to combine these two. So can somebody calculate that real quick? It's going to be a negative number now because this is minus 36.9659 because of the negative sign in front of the x up top, the 1 minus x. Can somebody calculate that real quick? So 34.96885 minus 36.9659. We can combine like terms and simplify this. It's going to be negative something. 1.99 what? What do you have? Is that what you got? Anybody? I don't see anything in the chat yet. So
Yes, sir.
All right, that's the x term. And then that's going to be plus 36.9659. Now we just need to solve for x. And this is equal to 35.453. Now we just need to subtract this from both sides. That's going to cancel that term on that side, and it's going to be this minus 36.9659. What do you got? Somebody subtract that real quick. That's also going to be a negative number.
Negative 1.5129.
So we're going to round that up and say 1.513 equals 1.99705x, right? Now we just need to solve for x. 1.99705. We're going to divide both sides by that. Somebody go ahead and put that in the calculator. And this is x. And then from here, we're going to figure these percentages out. Once we know x, we got it. It's a wrap after that. Right? The key is to understand which term to make x and which term to make 1 minus x, because the fractions have to add up to 1. So if I know x, the other term by default has to be 1 minus that to give me that second term. Anybody got that quotient yet? What you mean? Point seven something. Is that what you have?
Yep.
All right. And keep in mind, I fudged on this a little bit because I didn't acknowledge those negative signs, but there's a negative sign in front of both of these, right? So this is a negative, there's a negative sign here also. So you can just drop those, right? Or when you divide that negative 1.99, it's gonna cancel. So either way is fine, but you're not gonna get a negative number. So that is X. So that means that for the 35 isotope, with that, so let's just go ahead and finish this out. So that means that 35 chlorine 35 is 75 0.76% abundance. Is that right? Because all I'm doing is taking this number times 100 to get the percentage back. Let me fix that. It looks so sloppy. So 75.76. And what about 1 minus X? So this is X. 1 minus X is going to be what? 1 minus 0.75761. What does that give me? Is that right? 2424. If I round it, okay. So what that means is that the chlorine 37 is about 24.24% natural abundance. God dang it. Ran out of room again. 24.24%. So again, the approach to this problem is the fractions. We didn't have the fractions, so we got to find them. So one of those numbers is we made the fraction X, the one that's closest to the average. And then the other one, we made 1 minus X. After that, it's just algebra, multiplying and dividing. All right. So chlorine 37, 24%, chlorine 35, 75.76%. And again, it has to add up to 100. So if you add those two numbers together, it's going to add to 100. All right, questions about that? We got to stop there because we're out of time anyway. I apologize for going over a little bit, but I want to stop before we solve the problem. So any questions about anything? We're
Just have
going
one
to
quick question.
go right ahead.
What did you do with the negatives again? Why did you highlight those?
Because first of all, I forgot to, I didn't think about it when we were finishing that calculation. So I highlighted them to show that you could either drop them because both sides are negative,
Right.
or when you divide by that negative number, they're going to cancel each other anyway.
Okay.
Yeah, so you could do either or. If one side is negative and the other side is negative, you can either drop the signs, or when you do the division, they're going to cancel. The negatives are going to cancel.
Oh, thank you.
Yeah, no problem. All right. Any other questions about anything? I'm gonna clean this up, this bottom part up. I'll clean that up before I post these notes. All right. If not, let's log out. Hold up, something in the chat. Okay, I see you. We're gonna log out and we will be back tomorrow for recitation. The handout is already in Blackboard under the recitation handouts content area. So we're good. I just need to post this video and let me stop recording.